Have you wondered how to solve an ordinary differential equation that has matrices and vectors in it? In other words, you're solving multiple equations really at the same time. Well, that's what we're going to talk about today here at High Peak Education. Thank you for joining me. Coming at you with another video here, but this time a matrix ordinary differential equation video. So we're going to look at a problem that I recently encountered, which is the solution to a first-order linear ordinary differential equation with matrix or vector coefficients. That is to say, suppose I have the following equation. And by the way, the notation I'll use here is that whenever the arrow is over top of something, that's a vector. And in this case, it'll just be a two-dimensional column vector. So it'll be one column but two rows. So that's 2 by 1, 2 rows, 1 column. This matrix here is going to be 2 by 2. This is a vector x and this is a vector f. So suppose we want to solve the following ordinary differential equation where the prime here means derivative with respect to the independent variable. In this case, it's going to be time. Suppose this is the matrix A, and here we have the coefficients 4, 2, 3, -1 read across the rows. It's 2 by 2 square matrix. And the vector f, the function vector, is -15, -4, t times e to the -2t power. And this lowercase e here means Euler's number or the natural exponential. And we're just going to call that f0 ft. So f0 is sort of the column vector out front, and then ft is what's going to be this actual function of t. So how can we solve this ordinary differential equation? In order to solve this ordinary differential equation, we are going to solve equations 1, 2, and 3 that you saw above. Equation 1 was the statement of the differential equation. Equation 2 was the square matrix, and equation 3 was the function vector on the right-hand side. So let's make some definitions first here. And the vectors that are shown with the arrow symbol, again, are two-dimensional column matrices. Matrices are given by capital letters, so capital A and capital P will often be used in this problem. The prime indicates derivative with respect to a single independent variable, t. So thus, you could imagine that vector x is x1, x2 as a column, and these are functions of t, and then x prime of t is the time derivative of each of those component functions. So the method of solution that we're asked to use, and that is one of the more straightforward methods I could think of here, is going to be the method of undetermined coefficients. Now, if you have studied ordinary differential equations, sort of like a first course in differential equations, you have seen the method of undetermined coefficients to solve for a constant coefficient linear differential equation where there's an elementary function on the right-hand side. What do I mean by elementary function? So either a trigonometric function, an exponential function, or a polynomial, or some sort of combination of those functions, some sort of multiplication of those functions. However, if you're going to use this method in matrix form, the coefficients are now constant vectors. So that is constant vectors A and B and C vector in this problem. Furthermore, when you solve the homogeneous part of the differential equation, the homogeneous solution is actually going to not involve a characteristic equation, which typically you can factor and then get exponentials. It's still going to involve exponentials, but it's going to involve what we call a matrix exponential. So instead, we're going to be solving for eigenvalues of the matrix A, finding the associated eigenvectors, and allowing for the use of those exponentials. Okay, so what about this matrix method in solving an inhomogeneous, ordinary differential equation with constant coefficients of matrix A? So here we're going to first just set up the general formulas. So suppose we have this general differential equation. Vector x, which is the solution, is going to be the sum of the homogeneous and the particular solutions. So x vector is equal to x homogeneous plus x particular. And by the way, the subscript h and the subscript p will be used throughout this problem for homogeneous and particular. What do I mean by homogeneous? Well, if this vector f is 0, then the equation is homogeneous, because that basically means no matter what vector f happens to be, essentially you're just adding a constant number to both sides of the differential equation, and so the equation is still solved. That is to say, if you have vector x prime minus a vector x equals 0, homogeneous means 0 on one side of the equation. How about particular solution? A particular solution is a solution that x can be where it actually fits with vector f. Okay, so we'll go ahead and then talk about how to solve first for the homogeneous solution and then for the particular solution. So first here, the homogeneous solution. And this is when the vector function of time, that's f vector of t, is exactly 0. And this leads to effectively solving that there is a constant added to both sides of the equation such that the equation is still entirely valid. So what we're looking for is this following equation to be solved. X vector subscript h, that's homogeneous, prime is equal to a matrix x vector h for the subscript. Okay, now it turns out the solution to this homogeneous equation above, that's equation 8 here, involves a matrix exponential. And the matrix exponential is going to be e raised to the ta, so t being the independent variable, a being the matrix, and then this c vector just being a constant vector. So notice the constant vector here, just like all vectors, is shown to be a column vector. And notice that this matrix exponential involves, this is important, natural exponentials, that is, involving Euler's number, along the main diagonal, and the coefficients that multiply the independent variable t are the eigenvalues of the matrix A, that is lambda 1 and lambda 2. And then you have P matrix that multiplies from the left and P inverse matrix that multiplies from the right. So what do we mean by this? So here are the eigenvalues, and then matrix A here has to be an invertible square matrix. Invertible meaning that its determinant is non-zero, and what it also means is that you can find eigenvalues. So in other words, it's a non-singular matrix. Okay, so that's the idea. And then the constant vector, I already mentioned that. These, by the way, these constant values are determined typically from initial conditions or boundary conditions. Now this particular problem, if you remember the stating of this initial problem, doesn't give you initial or boundary conditions. So in general, for this problem, we won't be able to solve for C1 and C2. So those are arbitrary constants, just of the general solution, which again, you could usually find if you knew what x of t equals to some number was, some initial condition. Usually we take that to be t equal to 0. You can think about this like time equal to 0 if this was like a physics problem. And then what is this matrix P here? Matrix P is called the diagonalizing matrix. In other words, it's what makes this a matrix exponential. Now, does it make sense to you that not only do you have exponentials along the main diagonal, which are like exponentials that are solutions from the characteristic equation when we do the homogeneous solution if we have the method of undetermined coefficients. But notice that you could almost think about P matrix and P inverse matrix sort of canceling out, but it doesn't it turns out these P matrices depend upon the eigenvectors. What do I mean by that? Well, this diagonalizing matrix P is represented in terms of the eigenvectors, such that P is eigenvector 1 for its columns and eigenvector 2 for its columns, stated like so, such that the column space of this diagonalizing matrix are the eigenvectors. So the solution here with respect to the particular solution is going to be the following: that with the method of undetermined coefficients, the particular solution to the full matrix differential equation is often given by matching the form of the elementary function, that's ft. Notice that this is not f vector, so we're not worrying so much about the column vector out front, but sort of matching that function to the structure of the with a constant vector, such that a vector times sort of a matching function sort of goes along with f vector t. In other words, on the right hand side of this equation, I think we have t e to the minus 2t. And so that's going to be the first sort of elementary function that we're going to try to solve with. Where the details of this will be shown later, and the formulation structure matches the method of undetermined coefficients. Now, I want to mention there's a couple important caveats to solving this matrix ordinary differential equation. The first of all is unique eigenvectors. So one important caveat to solving this equation is, in the first place, the eigenvectors must not be identical for that diagonalizing matrix P to be defined. The eigenvalues need not be unique. You can have a repeated eigenvalue. You can have like a double root or multiplicity 2 of your eigenvalue. But if that's the same, then the matrix is actually going to be e to the lambda t, e to the lambda t along the diagonals, but it's going to be t times lambda in the upper right corner. And I'm not going through that problem here. So that's definitely possible. Another important caveat is that, what about the particular solution? If the particular solution matches the homogeneous solution in some way, then we will see that we will get something erroneous, like a vector is 0, which would cause the trivial solution to some particular solution that we're looking for, or a non-singular matrix which has no solution, something like that. So an important caveat for solving this is that we see in this problem is the particular solution matching the homogeneous solution. Now, by the way, that actually does occur in this problem. This complication can occur using the method of undetermined coefficients. As you will see, we will need to make the particular solution linearly independent of the homogeneous solution by multiplying by t. More detail will be given as we solve this problem. So, how do we get started in actually solving this problem? So first, we need to find the eigenvalues of matrix A. So in general, we can find constants that make the matrix A have a 0 determinant, so that the matrix is non-singular. So we subtract constant eigenvalues lambda along the main diagonal. Since the matrix A from equation 2, which was the definition of the matrix, has dimensions 2 by 2, that's rows by columns. It's a square matrix, and we can find those constant eigenvalues. The process is the determinant of A minus lambda I equals 0. So, not skipping any steps, we have the determinant of matrix A minus lambda I. Capital I is the identity matrix. That's 1s in the main diagonal, 0s everywhere else. And when we perform that, we use these vertical bars, meaning determinant of this matrix, 4 minus lambda, and then -1 minus lambda is what appears along the main diagonal now. And then the other entries are still the same. So we cross multiply with a minus. This is how we calculate a 2 by 2 determinant. So we have 4 minus lambda times -1 minus lambda minus 6. When we FOIL, that is, multiply out these binomials In terms, we have negative 4 minus 4 lambda plus lambda squared. And we should get lambda squared minus 3 lambda minus 10 when we formulate this as a quadratic. And this can factor to lambda plus 2 times lambda minus 5 by saying that two factors of negative 10 are positive 2 and negative 5 that also add up to negative 3. So we get lambda 1, as I'll label it, is negative 2, and then lambda 2 is equal to 5. So these are both eigenvalues that happen to be real numbers, they happen to be integers, and they are unique. So we'll solve for each eigenvector separately of the matrix A. So how do we find the associated eigenvectors of the matrix A? So in general, eigenvectors are found from inserting eigenvalues into the matrix A using row reduction of the matrix, which some of you know as Gaussian elimination. It's basically row reducing a matrix, and determining the corresponding non-singular form and finding the null space of that non-singular matrix. Then we find the corresponding vector direction that is unmoved in the matrix transformation of A. Some of you may remember that a matrix is really like a linear operation, and it's basically like some sort of rotation and stretching of space and that sort of thing. And it turns out that eigenvectors are only scaled by the eigenvalue, but the eigenvector direction does not change under the transformation. So that's why we're doing this sort of null space thing. So in other words, we're going to find one value of a vector direction will be a free variable, which we will take to be 1, number 1 for convenience, and then the other variable arises from the choice of that one free variable being 1. Okay, so let's look at eigenvector 1. That is x vector lambda 1. Okay, so what are we going to do? We're going to take the null space of 4 minus lambda 1, 3, and then 2, and then negative 1 minus lambda 1. So that is, we're going to take the determinant of lambda I minus a and make that equal to 0. And this lambda here is lambda 1. Okay, so by the way, the determinant of a minus lambda I is what we actually have written here. But because it's equal to 0, you could reverse that and call that the determinant of lambda I minus a. Now, by the way, I'm just going to set that equal to equation 13. That may seem kind of trivial that a minus lambda I and lambda I minus a both give 0, but this is an equation I want to tuck away for later. We'll come back to this at a much later point. So when we insert that eigenvector in here and we calculate this null space, we want the null space of 6, 2, 3, 1 as a matrix, which row reduces to 3, 1, 0, 0. Now when we have reduced our matrix to a non-singular matrix such that the null space equaling 0 is going to give us a vector that does not rotate but only scales, that is going to be, namely, our matrix that we need to find our eigenvector. So 3, 1, 0, 0 multiplied by x1, y1, sort of just think of these as the entries of our eigenvector, equals 0. Now when you multiply this out by matrix multiplication, then you have 3x1 plus y1 equals 0. Now the other equation would actually be 0 equals 0, which is exactly trivial, so we don't need that. So it turns out whenever you have an equation like this, you can't solve for x or y directly. But given that we know we formulated this in a certain way and we don't want the direction to change, only this to be scaled, we are free to choose one of those values. So for simplicity, let us choose x1 equal to 1. That means then y1 would be equal to negative 3. Notice that if I had chosen y1 to be 1, then x would have been negative 1/3. But notice that you're going to still end up with this, basically, if you multiply through by a constant. So whatever you end up with for your eigenvector, it ends up being, again, in the same direction, but just scaled. Now, here's the idea. This eigenvector, what that means is that vector direction does not change under the matrix transformation of the matrix A. How about eigenvector 2? It's a very similar process. You do A minus lambda I, but this time the lambda is lambda 2, which lambda 2 is 5. So 4 minus 5 gives -1. -1 minus 5 gives -6. -1, 2, and 3, -6 are across the rows of this matrix. Hopefully you can realize that row reducing this reduces to -1, 2 on the top row. So now calculating the null space, we should have -1, 2, 0, 0 times x2, y2 as a column vector. This is finding our eigenvector is equal to 0. And then when you multiply that out, you get negative x2 plus 2y2 equals 0. Now again, one of these variables is free. So for convenience, let's choose y2 equal to 1 this time. Then x2 is equal to 2. So that means that the second eigenvector is 2, 1. Okay, so now we have our eigenvectors. After having our eigenvectors, the reason we need that is because we need the matrix P, that is the diagonalizing matrix, and its inverse to be expressed in terms of the eigenvectors. So recall equation 10, which I showed above. Notice that the matrix P is going to be 1, -3, and 2, 1 for its column space. The columns of that matrix are the eigenvectors. And then notice we can find the inverse of this matrix with the following formula. So here is the equation for solving for the inverse of the matrix A. And notice that if you have entries A, B, C, D in a 2x2 square matrix, then you can calculate the inverse of matrix A by doing 1 over the determinant of A, that is 1 over AD minus BC, times the matrix D, -B, -C, and A. That is, you switch the entries on the main diagonal and you take the opposites of the entries across the main diagonal. By the way, notice that when you calculate this inverse of the matrix A times its inverse, or inverse times the matrix A, gives the identity matrix, which in matrix form is just the number 1. So when you calculate this for the matrix P that we had above, we switch these entries, which they just switch to 1, 1, and then we switch these entries and take opposites. So we have 1, -2, and 3, 1, and the determinant of that matrix is 7, so it's 1 over 7 goes out front. Now, by the way, you could multiply the 1 over 7 in here to each of these entries, but as we'll see, it's going to be more convenient to leave our coefficients out front. By the way, that's a good problem-solving strategy, to kind of leave things out front early on and let them collapse later. That way there's sort of like this memory of where things came from. Okay, the next thing we want to do is actually calculate the matrix exponential, e raised to the A being the matrix A, using P matrix and P inverse, and the eigenvalues. So we'll do that here. So in order to calculate this matrix exponential, we're going to recall the formula for the matrix exponential, which was equation 9 a ways ago. And this is set up to be P times that, again, matrix with exponentials along the main diagonal, lambda 1 and lambda 2. And then notice that P inverse is here. So we put those matrices in. Don't forget that 1/7 from the determinant from the inverse. So let's put that 1/7 out front. Now when you take this first matrix and multiply by this set of exponentials, you get this set of exponentials as a square matrix. By the way, notice that you need to know how to use matrix multiplication here. Okay, so I'm not going to go over that. This is a well-known thing from linear algebra. See other videos and other resources for that. Then we should take this square matrix and multiply by the P inverse, so we get all of these values. So it looks like 1/7 is out front. Notice that we have exponentials involving e to the minus 2t, e to the 5t. Notice that lambda 1 was negative 2, lambda 2 was 5. Also notice that we have sums of each of those exponentials. Some are positive, some are negative, and the 1/7 is out front that came from the determinant. And there we go. So now we're very close to the homogeneous solution to this problem. We should be able to take this matrix exponential and basically multiply it by a constant column vector. Now taking that matrix exponential and multiplying by a constant column vector, that is a constant, we have again 1/7 times that large matrix we ended up with that involves exponentials times this column vector, C1, C2. And by the way, here's an interesting trick we can do, and again, this is why you shouldn't collapse things too quickly. We can just write this without the 1/7 and still the C1, C2. Now you may say, where did the 1/7 go? Well, it turns out the 1/7 basically got absorbed into this C1 and C2. What do I mean by absorbed? Well, if we redefine these constant values, C1 and C2, such that they are 7 times their original amount, that gets rid of the 1/7. But remember, we don't actually know what C1 and C2 are. They're just constants. So we can actually just multiply that 1/7 in and just arbitrarily sort of redefine C1 and C2. We're not going to know what C1 and C2 are unless we had something like an initial condition. So this makes the homogeneous solution a lot nicer. Notice that we now have the homogeneous solution. In some sense, we have half of our whole solution to this matrix problem. Now, in order to continue solving this, we want to move on to the particular solution of the problem. Now let's talk about the first and second guess of the particular solution, using the method of undetermined coefficients. Using the method of undetermined coefficients, our first guess follows the form of the function f0t from the equation 3 above. With constant vectors a vector and b vector, the form seems like it should be x vector subscript p, that's particular, is equal to a vector t plus b vector. So that's some arbitrary first order polynomial with vector coefficients. So that's a vector t and b vector times e to the minus 2t, because e to the minus 2t shows up on the right hand side of the equation. So this is what we're going to call equation 20. However, if you compare the first guess of the method of undetermined coefficients in equation 20 above to the homogeneous solution in equation 19 above, the first guess, especially as it goes along with vector b, solves the homogeneous equation. What do I mean by that? If vector b happened to become the same exact number as one of these exponentials, namely e to the minus 2t, do you see that e to the minus 2t and this vector b could become, say, 1, negative 2, or it could become negative 3, negative 3, and notice that that would exactly be the exact same solution as the homogeneous. So we don't want to repeat the homogeneous and the particular, because then it's not really a particular solution, it's not unique. So what we should do is, this sometimes happens with the method of undetermined coefficients. So how do we carefully write out the form of the particular solution for this problem? Well, we're going to first look at the first guess, and as you'll see, the second guess for the particular solution using the method of undetermined coefficients. So using the method of undetermined coefficients, our first guess follows the form of the function f0t from the equation 3 above. With constant vectors a vector and b vector, the form seems like it should be x particular vector is equal to a vector t plus b vector multiplied by e to the minus 2t. Let's think about why that is. A vector t plus b vector is a general first order polynomial with vector coefficients times this exponential. That appears on the right hand side of the equation, namely having to do with the function, the particular function, since this is a non-homogeneous problem, the f vector. However, compare the first guess of the method of undetermined coefficients in equation 20 to the above homogeneous solution in equation 19. Note that the first guess with vector b also solves the homogeneous equation. So think about this. If we have b vector e to the minus 2t, if it has the same coefficients as we see in the matrix above, then we're double counting, and the solution really isn't a particular solution because we're just getting the exact same solution. So the form of the solution we will use at first should be linearly independent from the homogeneous solution. In other words, we need to multiply by the independent variable t to make this linearly independent from anything that is in the homogeneous solution. Now, by the way, this method I think was first discovered by Euler, but it's certainly a well-known method when it comes to the method of undetermined coefficients about whenever your particular solution matches the homogeneous solution. So this is what we have. So this form of the equation 21 above, we will insert into the original differential equation. So now let's look at this second guess for the particular solution. In order to get the second guess for the particular solution, we need this particular solution, but we also need its time derivative. Well, that is its derivative with respect to t, the independent variable. So what is this thing's derivative with respect to t of the second guess? Well, we need to use the product rule on each of the terms. So we should have 2a vector t e to the minus 2t, that's the derivative of the first term, leaving the second term alone, minus 2a vector t squared e to the minus 2t, that's the derivative of the exponential. But then we also have the b term, so we have b vector e to the minus 2t, that's the derivative of the first term, the t, and then we have minus 2b vector t e to the minus 2t. That's the derivative of the exponential. Okay, we have to insert this into the original differential equation. So this kind of gets a little long. So we take equation 22 and we put it into equation 1. That's the entire left-hand side. That's just x prime, namely x vector prime subscript p, the particular solution. So there it is. Then here is the matrix A. Then here is x vector p, that is the particular solution, second guess. So it's a vector t squared plus b vector t e to the minus 2t, and then plus this f vector. So this is minus 15 minus 4 t e to the minus 2t. Okay, notice that e to the minus 2t is in every single term, so we can divide that throughout. And then we can split into actually 3 equations. I have 2 equations here. It'll really be 2 important equations that we get solutions from, but really 3 equations, as we'll see. So here, to get started, we have eliminated all the e to the minus 2t parts. And furthermore, we also are starting to take a look at what parts are the same. So this is a t squared term, this is a t squared term. We'll equate those. Here are linear t terms, these 2 and then these 2, so we'll equate those on the next slide. And then b vector, I don't see any constants over here, so we'll equate it to the 0 column matrix. Now, when we equate these t squared terms, we have 2a vector t squared equals matrix A vector t squared. By the way, one of the things I did between the last line and this line here is I did multiply the matrix A, capital A, into at squared plus bt. That was x particular vector. Okay? I had to multiply it in from the left though, because remember, when you multiply matrices, we cannot commute things. commutation is not just like it is in numbers multiplication or just variables multiplication. Okay, so anyway, we can divide out the t squareds, and because there's a matrix here, I'm going to put 2 times the identity matrix because I think that'll be a little more straightforward. Because the identity matrix times vector A is the same thing as vector A, and that way we can solve really nicely here. Well, if we subtract this matrix over with a minus, what's left on the right-hand side should be 2 rows, 1 column, namely the 0 vector of that size. When we multiply 2 in here, we have 2's in the main diagonal, minus the matrix 4, 2, 3, negative 1. We should get this. That's negative 2, negative 2, negative 3, 3. We can multiply everything by negative 1, switch the sign, there we go. And it turns out this matrix, without showing the step, does have an inverse. Now, by the way, I didn't mention this before. You can certainly use the formula I showed you to find the inverse of this 2 by 2 square matrix. Also, you can use a piece of software. With a lot of this matrix stuff, I would recommend a piece of software like a Texas Instruments calculator, or you could use MATLAB, Mathematica, Python, something like that, and this should be able to give you one of these things. Wolfram Alpha will also do it, that sort of thing. But anyway, when we have this matrix that's singular, that has an inverse and has a non-zero determinant, that means the matrix A would have to be 0. So that doesn't seem right. That doesn't seem very useful, because the matrix A seems to be like something we're solving for. So let's put that on the back burner and let's see if we can get some more information from the other 2 equations. And as it turns out, the information that we get from the other 2 equations really does help us. Namely, what we get is we get, for the t equation, 2at minus 2bt, a and b here are vectors, equals matrix A times bt, b vector t, plus this f0, so that was the coefficient on the matrix F, times t. Well, it turns out that we can eliminate the t's across the equation. So we have 2a vector minus b vector is equal to, and it turns out it's going to be negative 15, negative 4. Well, why is that? Well, it's because if we just look at the constants equation, b vector is equal to the 0 vector, we can insert 0 here for b on either the left-hand side or the right-hand side. So we just get 2 times vector a is equal to negative 15 over 4. So we can pull out a negative 1/2 by division times this column vector, and there it is. So it turns out that a vector does not seem to just be the trivial solution, but a and b seem to be given by these column vectors. So now we can finally write our full solution. Now, before we do that, I want to discuss an important caveat. And it turns out what would have happened to you if you had not multiplied the first guess through by t, the independent variable, to make it linearly independent. So here's an important note in a discussion of non-singular matrices. Observe the first guess equation above. That first guess equation above, in terms of the constant coefficient vector b, throughout would have given you something nonsensical. Note that you would have found this result. So if you'd have walked yourself through all the steps, and by the way, I did this problem several times to make sure the answer is correct. If you'd walked yourself through there, you'd have gotten 6, 2, 3, 1, which actually leads to 3, 1, 0, 0 equals this vector on the right-hand side, that 15, 4 vector. And it turns out that that's a determinant of lambda 1i minus a. Remember, that was equation 13 I said a long time ago we would come back to, equals 0. But notice that that's only true if a here is an eigenvector, which really is just like the homogeneous solution. So it turns out, really the second guess equation is correct. You're going to end up with something right here that is erroneous. That is a nonsensical result, that is a non-singular matrix, if you go through many other ways to do this problem, namely things that are not linearly independent. We have to have linear independence. This occurs when the method of undetermined coefficients happens so that we have to multiply by the independent variable to 1 power larger. In other words, the particular solution cannot match the homogeneous solution. So essentially the first guess equation must be multiplied by t. Okay, to form equation 21. Now let's assemble our full solution from the homogeneous and the particular. So now finally we assemble the homogeneous and the particular solutions together to get the full solution of this matrix ordinary differential equation that is inhomogeneous but have constant vector coefficients or matrix coefficients. So recall the homogeneous equation solution from equation 19, that was much earlier, that involved the matrix exponential. Also note the particular solution we have just found in the constant vectors a vector, b vector, and the second particular solution guess using the method of undetermined coefficients. Those are equations 24, 25, and 21. Combine all four of these together in the full solution. So the homogeneous vector x plus the particular vector x, these are each solutions, and by the way, they're functions of t, the independent variable, given by this matrix of exponentials times the constant vector, which would be determined from, say, initial conditions. That is, you have to know what the value of the vector x was at some time t. So like some initial condition, maybe t equals 0 or something, you could find c1 and c2. But in general, they're just unknown. That's part of the general solution. That comes from the homogeneous solution. And then here's the particular solution. -1/2 times this column vector, 15, 4, and this function t e to the minus 2t. You can multiply these out, and what you get is you get this matrix, that is this column vector, because it's a 2 by 2 matrix times a 2 by 1 column vector. And then if you multiply -1/2 into this column vector as well as these functions, we get what we see right here. And if you just add them, just literally adding the components, you can even factor out a c1 if you like and a c2 if you like and some coefficients. But this is as good as the final answer is going to look like for the final vector x as a function of t. Notice now we have a single column vector, 2 rows, and 1 column, so 2 by 1. So this finally ends the problem. Thank you very much for watching High Peak Education. Please smash that like button if you enjoy this content. Please subscribe to the channel and share this amongst your social networks to grow the channel. I look forward to reading your comments as well, and I will see you in the next video.